Hey, Tony, thank you for coming in.
My pleasure.
You know, I've been following this space for such a long time, and even back in 2015, I was profiling to this group of 100 CEOs that this is something you have to pay attention to, and guess what? I mean, it's now I would say the majority, not everybody, the majority agree that it's in the not the 2100 or 2050, but it's more in the nearer term of actually getting some kinds of at least niche applications and then the broader sort of universal
Sure.
quantum computing as well. But you definitely are leading in this space. I was following your Honeywell work. I was That was really, really great work. And then to do this Quantinuum work, I mean, it just consolidates your leadership. So really, thank you for coming in to share this unscripted dialogue with me, and we'll just see where this goes. So,
Outstanding. Well, happy to participate in this. Very pleased to be invited. So love it. Let's get through it.
so Tony, my audience has scientists and engineers, but would you believe the top four positions are investors, board members, CEOs, and founders, and things like that. So, and I do have some students as well, things, but generally it's really senior people that are my principal audience. And the question they always ask me is, you interview these amazing people, and Tony, you're definitely an outstanding individual. So they're always curious, what are two or three inflection points that made this wonderful career that you had? You've got this engineering degree from Minnesota, which is a really good school, and then you got an MBA from Kellogg, again a great school, and then you got this background in math and at Boston Consulting Group, and then Honeywell, and then of course what you're doing now. So, and maybe these inflection points happened when you were 3 or 5, and it could have been some kind of mentor when you were younger. It could have come from your family. Can you highlight two or three that kind of shaped this wonderful career you have and you as a person?
Yeah, no, I appreciate it. So I saw the movie The Right Stuff when I was a kid and decided I wanted to be an astronaut. And that happened. People see movies or they see things and they're like, I want to do that. And then maybe a week later they want to be something else. Nope, that's it's stuck in my head. That's what I was going to go do. And I got closer than most. So was able to go and spend a decade of my life working for NASA at the Johnson Space Center. Happened to be the operations manager of the facility that trains astronauts how to do spacewalks. Um, Fabulous part of my both life and career. But it started something that has since been able to be replicated, which is when the mission is so much more important than the person. When what you're trying to achieve has an impact on humanity, it just resonated with me. It was something where um, you know every job is important, but you want to give meaning. You want to give meaning to your life. You want to give meaning to the world, and there are fewer times where that's possible. But it started with NASA, where I could feel personally like I was contributing to humanity's success in science and technology. Uh, I then went to the Boston Consulting Group, and what I focused on was engineering product companies. And so it was industrial goods, it was med tech, it was consumer durables, it was kind of the tech space where it was very tangible. Like I could see and pick up what it was that those clients were trying to go do, but it also allowed me to then see the kinds of problems that these large companies face, and they're extremely challenging. And I became kind of known for when we haven't done something before, let's give it to Tony. And so my own personal practice area was a white sheet of paper, start from scratch, first principles view of things. And so between those two parts of my career, it was very big mission oriented and what can we do from first principles. And then I came into Honeywell. And when I came into Honeywell, I led marketing and strategy for Honeywell's biggest division at the time. So an $18 billion revenue division called Automation and Control Solutions. And it turned out that in that role, I also had some scientists that were reporting into me, and they were doing these incredible things across cryogenics and magnetic field systems and ultra high precision control systems and lasers and photonics. And it was these brilliant people who said, do you know what we could do if we put all these things together? And the three connected then. My ability to do first principles business building with kind of the mission inspiration that could drive humanity, combined with now some brilliant people, where it's like we can make this happen. We can not only be at the beginning of a new technology, we can really help shape how this ends up getting adopted by the world. So it was almost like a calling, I guess.
I can see the value of the NASA. So it's a really big picture, and of course your educational background fits as well, right? And you know, you have a BSc in mechanical engineering, and then you get into the consulting group, so that adds really the sort of the really practical business delivery elements, but still involved in tech in some way, right? And I can see how the MBA from Kellogg would help in that as well, right? So, and then you get this huge opportunity and with Honeywell, and it's really the confluence of all of these pieces coming together, and then you're kind of going back to this big you know, transformational stuff with the Honeywell solutions and working in the quantum space. Can you now talk about the evolution into Quantinuum, or
Yep.
what's the proper pronunciation?
It's Quantinuum.
So how did that come about?
You know, this is also great, and it's the way I think businesses should evolve. So I was at the time the president of Honeywell Quantum Solutions, so this division inside of Honeywell that had been charged with designing, developing, and making trapped ion quantum computers, and we were working with everybody in the ecosystem, everybody that we could come across, get our hands on from a application and software development standpoint. And there's just brilliant people everywhere. But there was a company that was just, we meshed with so well and had actual products, even at this day in this technology. And we started working with them more and more. They became heavy users of our H-series quantum computers. Our technical teams interacted and started gelling with each other. And then very importantly, the person who was the founder and CEO of Cambridge Quantum and I, we got along. And it turned out that our philosophy was very similar, which is this is going to be transformative to humanity. And by this, I mean quantum computing. Quantum computing is going to transform humanity. The question is, at what time scale? At what time scale is it going to happen? And we had a collective belief, and that is, if we got together, we could accelerate how fast it really does happen. Which is, it goes past audacious into a little bit of a, are you sure? But it was beyond ideas. We actually had real products that we could make happen immediately that would start to showcase how valuable quantum computing can be to the world. And so after enough talk of what we could do, we decided to do that. So between Honeywell and Cambridge Quantum Computing, we jointly formed Quantinuum, and we're a private company. We do have a majority shareholder, and that is Honeywell. So in the combination, Honeywell retained 54% of the ownership. And we have been now on our journey for the last 18 months of being Quantinuum and helping to accelerate quantum computing's impact.
I remember, you know, a few years ago, I guess it was maybe 2019, where Google announced this quantum supremacy, and of course, IBM was challenging it, and it was like not a practical problem, but just showing the capability. And then the Chinese have done something similar, and so on. And you can see these different players, and of course, D-Wave has always been on that niche area and have been out there for some time, and you get these different players coming in. And then out of the blue came Honeywell, and you were getting amazing results and using the measurement that IBM has been using, this quantum volume idea, and which is a better measure than the traditional. But there's many players out there now. I'm probably counting over 200, maybe it's even bigger. So before we start mining what the ecosystem is, let's talk about this trap ion technology and electromagnetic fields as qubits, and you're using laser-induced interactions, and so you're going to have longer coherence times and high fidelity. Let's talk about that. And your full stack as well. You're not just the hardware, your software, and you even have this software development kit, and you're even in natural language processing with your Lambeq product and your chemical simulation. I mean, you are really the entire ecosystem in one company. And also you have the H series, which is just getting in, just really amazing results, right? So let's mine some of that. So first of all, trap ion, what does that mean to the CEOs out there that are thinking, you know what, I've got to get on this road now, because you can't just catch up next day. You got to start playing with it, right? And start looking at how this works and building your teams and making sure that you can ingest this thing so it's practical. So what is trap ion, and why is it better, do you think, than some of the other systems out there? And then we'll get into other areas of your stack. So
sure. And actually, I'm gonna start in probably a slightly odd place for you, maybe, for this conversation, but it's how I feel and what we do, which is we as Quantinuum are very platform inclusive. We're one of the biggest users of other people's quantum computers in the world, and we are because we're experts. We have 500 people in our company around the world that are quantum computing experts. And so I am one of probably a fairly small group of people who believe that there are going to be multiple technologies that continue to evolve in quantum computing. And it's the reason I believe that is because some of these different underlying technologies have properties that are better. It's always a trade-off. What are you trading off? Now, we picked trapped ion back in 2010. And we picked it because our belief was that the quality of the qubit, these underlying building blocks of quantum computation, would matter most, particularly in the first era of quantum computing. So call it this first decade, the 2020s, we believe that quality would matter most. And what you get when you use a individual ion, so for those who are non-technical, we use an atom where we've stripped off an electron and it becomes a charged particle, an ion. So our computational building block is a infinitesimally small piece, an actual atom. I used to say, and this is kind of an interesting exercise, if you were to hold your hands up like little bunny ears and cup them together, inside of that space is a trillion atoms. That's what is collected now in my hands. And so imagine taking individual ones and saying, I'm going to turn you into my computational device. And it turns out that this is science physics that has been proven for many decades, which is why everybody always said, well, quantum computing is 10 years away. And they've been saying that for every 10 years, maybe even every year, for about 50 years. It turns out, as you might imagine, it is really hard to control. How do you control these individual atoms? And so we took an approach where we physically move our ions, our trapped ions, around. And the reason we call them trapped is because once they have a charge, Now you can use an electromagnetic field to hold it. So imagine this little, looks like a, think of it as a marble, and would roll around. And so you create an electric field that is ultimately just holding it in one spot. And what we will do is try to move those individual ions now together to be able to do our quantum operations, to be able to do things like entangling them and putting these ions into a superposition, and that superposition and entanglement, those are the two of the three principal superpowers of a quantum computer, and they're the building blocks that you would need to go do. And because every single one of these atoms is identical, you get to start with something that we would call a perfect quantum bit, a perfect qubit. And anything that then is an error, something that would reduce the accuracy of your system, is because of the system that you put around it, as opposed to that perfect qubit itself. And one of the things that, if people know Honeywell, one of the things that they know Honeywell for is it is one of the biggest complex system integrators in the world. And it is that way because of its control capabilities, its ability to do these precision controls in aerospace and defense, in big process chemical plants, even in buildings. Doing that control is what makes it really effective. Honeywell as a company. And in terms of quantum computing, regardless of however you're doing it, starts as a physics problem and then migrates to a controls problem. And so our approach was, let's solve the controls problem first. Physics can handle itself. Let's solve the controls problem first. And then if we can do that, then we'll start to bring it forward as a quantum computer. And we have been exceptionally successful in doing that.
So you talked about superposition and entanglement, and then there's a sort of third characteristic. Can you define that sort of layman terms?
Sure.
Superposition and entanglement and this other characteristic. And then your laser-induced interactions. What does that mean?
So I always call it the three superpowers of quantum computing. What makes a quantum computer do what a quantum computer does? And it starts with this idea of a superposition. So if you are using a classical computer, that classical computer has a bit, and you have, talk about multiple bits, but that bit is either a 0 at any given time or a 1. It's either on or off. It's a 0 or a 1. Whereas a quantum bit, a qubit, can be both a 0 and a 1 at the same time. And in fact, it's described usually as a sphere, where 1 might be fully up and 0 might be fully down, but you can actually put that qubit into any position along 0 and 1, and that is a superposition. So you can think of it as it has both of those two answers at the same time. So then you get the next superpower, and that's called entanglement. So I have multiple qubits, and I want to impart information so that those two stay connected. They stay correlated, and there's an answer that both of them will help you detect as you go on. And so you can do these operations where you're bringing multiple qubits together, entangling them, and then as you move through the rest of the computation, those two, despite being separated in space and being separated in time, continue to share information about each other. And then the third superpower is called interference. And think of it as a wave. So if you were to do a wave and it was the exact same frequency and it was coming together, it would cancel each other out so that this wave would become just completely flat. That is destructive interference. Whereas you have constructive interference, which is I get it to the point where it makes an even bigger wave. And that idea of interference can actually be programmed into a quantum computer. So why would you program it into a quantum computer? Because it turns out that if you take advantage of those three things, the superposition, the entanglement, and the interference, if you have something like 10 quantum bits, those 10 quantum bits during the computation can take on over 1,000 values. If you move from just 10 to 50 quantum bits, those 50 can now take on 1.1 quadrillion values. At 10, it goes from 1,000 to 50, it's 1.1 quadrillion values. And it's evaluating all 1.1 quadrillion values at the same time. And what you use then is interference to give you the answer, the one answer that you really wanted out of that entire set of information. That's what gives quantum computers their power, is that it's not that they're faster than classical computers, they just process information differently. And we're not going to use quantum computers to do Excel. That's not what they do. But if you wanted to find information about a set of data, and let's imagine you wanted to know what the absolute maximum point was. Think of it as a map, topographical map, where you have all these mountains and all these different places and valleys, and you wanted to find the one that was the absolute highest. That is what a quantum computer does exceptionally well. And so those kinds of problems then can get mapped to real world use cases. Like that is an optimization problem. I can find quantum computers to help do some type of optimization. I can help use a quantum computer to represent, simulate another quantum thing. So what is another quantum thing? The human body, molecules, life-saving drugs as they're being developed. You have to think about the molecule and how it's going to interact with its surroundings, and thinking about a future quantum computer that can help do that simulation. That's really what excites the whole world about what quantum computing can do.
So from your explanation then is you're really saying that quantum computing and this idea of entanglement and superposition and interference gives us sort of this massive parallelism that doesn't exist even at the classical sense. You can get some of it at the classical, but it's very awkward and doesn't scale, where you get this exponential scaling that's 2 to the n scaling. And so 2 to the n is sort of the capability of 10 qubits, and you go 50 is 2 to the 50th. And that's an exponential increase of scaling capability of simultaneously addressing a very complex problem all at the same time, right? So, and that's I guess that's the superpower. Did I get that right? The super.
Absolutely. And then one of the things, and this is happening particularly in this early era of quantum computing, is that, well, then every time we had qubits, isn't that just great? Isn't that the best thing we could possibly do? And the answer, unfortunately, is it depends. You'd think it would be, but there are errors. That this quantum computing in general is what we call a probabilistic, which is, there's a probability distribution of answers. And what you're really trying to do is get to the answer that has the highest probability, that's the one that's leading you to the answer. But in this era, as people, including ourselves, are developing quantum computers, there's noise. And this noise gets propagated when you start to have interactions with multiple qubits. And depending upon the system, that noise propagates so fast that you actually can't take advantage of all of the qubits. So you may say, I have 100, or I have 400, or I have 1,000. Well, isn't that great? No, because you actually can't take advantage of all of those 100 or 400 or 1,000 qubits. Which is why, if I rewind a second and say, why did we focus on quality first? Because that's where you actually can get the power of each qubit as you start to put them in. And you mentioned earlier this idea of quantum volume. It was precisely for this reason. It was precisely for how do you measure, how do you benchmark a system as it increases in performance by both adding the number of quantum bits, qubits, but also reducing this error, reducing this noise so that you can get the most benefit from that computation. It takes both of those two pieces to actually have a quantum computer truly function.
I'm just thinking, and maybe I got this wrong, the numbers are now getting so large, even with quantum volume, that I think IonQ does a log function of the quantum volume, something like that, to keep the numbers smaller, or maybe it's another group.
Yeah, no, it does come from that kind of formula you mentioned, which is 2 to the n, right? If you think about the value of a quantum computer is that it scales exponentially. So, 2 to the first, 2 to the 10, and that's where you get to this 1,000. When you get to 2 to the 20, now you're at 1,000,000. And so in order to keep the numbers smaller, you could say, well, I have this many effective qubits. So that's what quantum volume did, was say, how many effective qubits do you really have? And then if you do that log function, 2 to that number, then you get the quantum volume number, which is why that keeps on increasing the way it does. But ultimately, it is a real question of, you may have a certain number of qubits in your system. How many can you really use to go get something done? And then to everybody, what everybody cares about is that valuable? Does that actually help you do something today? Or will it take more of these qubits at a certain quality to do another type of to create an answer for something that we all care about? It could be to help develop a new life-saving drug. It could be to help do optimization of your financial portfolio. It really depends on the kinds of problems that we can go solve with how that system is performing.
Every time you answer a question, then it's kind of, I get flooded with a number of other questions. I'm going to do a bit of a time check because this is unscripted. So, are you bound by? I'm at 9:31 Pacific time. Are you bound to 10, or can you go beyond?
I think I'm bound to 10, but
Okay.
yeah.
That'll determine then how deep I go into some of these questions. Okay. Um, Okay, so you talked about the 8 series in the Quantinuum product line, and that's where you're really getting to some practical magic, right? From a scaling standpoint.
Sure.
That's my understanding. Can you talk about why the 8 series is so important? And is there some other series coming up that's even going to, we're just going to be amazed, right? So.
I think we're going to keep on referring to all of the generations as the H series. So we have 2 commercial quantum computers today, and they're the first generation. So we call them H1. And then, because I don't have any other fanfare for naming things other than Quantinuum, we call them the H1-1 and the H1-2. So we have 2 versions of our first generation. The way we decided to build quantum computers was actually not focusing on a generation by generation sequence. It was actually focusing on an end future state. So we sometimes, if you've seen our, or if anybody goes online and looks at what our roadmap is, we show something that we call the H5. And everything was designed around creating this H5, this fully fault tolerant universal quantum computer that exists at the end of the decade. Because of Honeywell's history, its legacy of how you do product development, then you work backwards from what you ultimately want to create to say, what do I have to have proven to myself that I can do at each kind of next stage to be able to get there? And so our roadmap actually is just an enumeration of, from H1 to H2 to H3 to H4, these are the building blocks that you have to go do to validate that you can build an H5. And it turned out that as we were thinking about that, these computers were very valuable to people already. So when we launched and this is an entire approach of how we do our H series, which is, when we launched our H1, our first H series device, we purposefully launched it at less than 0.01% of its full capability. And You go, well, who does that? Who would purposefully launch a device at less than 0.01% of its full capability? Because it was still the highest performing quantum computer in the world at that point. And so what we decided to do in collaboration with our customers was say, okay, we're going to now do an approach where we put it online for you. And then every 2 weeks, we take it down to do some type of improvement to it, and then put it back on for 2 weeks, and then take it down for 2 weeks. And the reason why we have two is because now as we stagger that, there can always be one of our first generation online as the other one is going through its upgrade cycle. And in that time period, and that's why we're measuring things like quantum volume, we've already seen it go now two, and we're closing in on the third order of magnitude jump in 3 years. So we started at a quantum volume of 64. Within a year, we were at 640. Within 2 years, we're at 6,400. And we are very close to delivering on our 64,000 quantum volume, because we can keep on making these improvements to this system, the exact same system. And so the way we do this with many of our customers is it's a subscription. You have a service, and think of it as you have Netflix, and you're subscribing to Netflix, and a year from now, it's 10 times better than it was. And 2 years from now, it's 100 times better than it was. And 3 years from now, it's 1,000 times better than it was. Like, you wish, right? You wish Netflix worked like that. But that is the way quantum computers can work. And so we've been able to deliver on that. And what we are very closely moving towards is our release of our second generation, which we already use today. We operate on it. And just as a matter of course, when you have 500 quantum computing experts, you know what to go do with these systems. So we have the ability to run it, use it, make sure it's operating at a level of performance that we are proud of. And then we can be in a place where we can release that to the rest of the world and to our customers. So this whole idea of generational changes allows us to put in place systems that currently have very high value because they are the highest performing, but upgrade them in real time so that customers can continue to have the best available system for whatever research they're doing. And it could be a JP Morgan Chase that's doing work on portfolio optimization or fraud detection. It could be an Oak Ridge that's doing work on, thinking about, U.S. government energy related things. Anywhere for Honeywell, thinking about the next development of a new refrigerant molecule for its performance materials business. So all work that can be done kind of collaboratively and at the same time as these systems get higher and higher performing.
I mean, that's really fascinating. I mean, your H1-1 is what, 32K. So are you saying the H2-1 will be 64K? Is that what you're saying, or can't you say yet?
I'm holding off on saying, because one of the things that we've done, and hopefully if anyone's followed me, you'll see that we are very careful to say this is what we've done. We try to avoid hype at all costs, because in this industry, this technology, and especially at this time, it's really easy to think about all the future wonderful things that these systems are going to go do. And I do that too. Like it's inspiring, but it's also going to play out over time. And so we're very careful to say, this is what it does right now. And we have proof that this is what it does right now. So we will, the time frame is short. I will say it's very soon that we're going to be doing this, and that we will have collaborative data that supports exactly what we've done and how we've done it.
Well, I mean, I'm excited to see H5.
You both.
Right? Universal quantum computing. I mean, that's sort of like the holy grail, right? So, and it's stable. Where you can solve any or work on any kind of big optimization problem, or something that has to do with nature, right? Because the quantum computing and nature is just sort of intermeshed so well. Okay, let's talk a little bit about the software side. So you're not just the hardware. Can you talk about your open source toolkit and why you produced it and what people are using it for? And then after that, you've expanded that into the tools for quantum chemistry and natural language processing. So first of all, your open source and it's platform agnostic, right?
Yep. Yeah, we about almost 2 years ago now, open sourced a software library that's called Ticket, T-K-E-T. And like any good software, any good product that's made, it was built because we needed it. And why did we need it? We needed it because, as I mentioned before, we use a lot of people's quantum computers. And as you're developing algorithms for a quantum computer, it's really hard. It's really hard to make these algorithms, particularly, it's hard to make them efficient. And so what Ticket does is it automatically optimizes somebody's quantum circuit, their quantum algorithm. Think of it that way. Because you don't know, well, do I have to have all these gates in this way, or do I have to have all the kind of the interaction that's actually going on with qubits in these various systems sometimes is a little oblique. And being able to have something that just automatically does that for you is outstanding. But then you have to worry, well, did I just lock myself into something? And so, because again, we use so many people's quantum computers, we didn't want to be locked into anything either. So we made it portable so that the same software algorithm that gets optimized here can run on everybody else's backend. And it doesn't do away with other people's software. In fact, it's designed to work seamlessly with that software. So if you're IBM and you have Qiskit, it works seamlessly with Qiskit. If you're Google and you have Circ, it works seamlessly with Circ. If you are Microsoft and you develop Q Sharp, it works seamlessly with Q Sharp. So now, if I'm somewhere in Indonesia and I want to get into quantum computing, what do I use as something to help me do that work where I can write an algorithm and it can work on everybody's quantum computer and it works in an optimized way? Ticket. And we decided to do it open source because this is the beginning. We want people to get good at this. It's hard. It's very hard. And there just aren't that many people in the world who have built up an expertise to go do it. Which it's incredible. Like we are at 1 million downloads, 1 million downloads of Ticket. Now, I don't know what that means in terms of actual users. I don't. It could be more than that because you have people who are using this and trying to figure things out, or it could be less than that because what we found is that you end up having super users. So you may have a couple people dabbling, but for every 100 people dabbling, you might have 10 people who are really starting to get spend a lot of time and resources. And then what we did, again, we built it because we needed it, is Ticket is already then built into all of our software applications. So our cyber application, our chemistry application, our Monte Carlo application, and it's built into our hardware stack. So Ticket has been, we have the ability to think about it the way an Apple would think about it, where they have the device, they have the operating system, and they have the application. And so you can make sure that all of that is optimized. And so we optimize it for ourselves and we make it extremely useful for all the rest of the systems that are out there.
And then you got this quantum natural language processing, Lambeq, I guess.
Yeah, and I tell you what, we have so many exciting things. There's so many exciting things. This is one of those where it could just be an absolute game changer when it comes to AI. If there's so much talk right now about AI and what AI can do and what both now and in the future, but one of the things that ends up coming up over and over again is the black box nature of how the AI is actually working. What is it that is recursively being built into the idea that that's happening? Lambeq is for quantum natural language processing. And we opened it up as an open source toolkit to the world because we believe in a future where it is completely transparent what is happening for AI. It is very, very clear. And in fact, it was designed by our chief scientist, Bob Kuka. Steve Clark, formerly of DeepMind, is a big part of building out this capability. And we even think this is probably in the last half of the decade away in terms of when you're going to be able to really take advantage of quantum computers when they have gotten to that level of performance. But like anything else that's worth spending time on, the impact of this could be so big that we want people from all over the world to be spending that time, spending that energy to look at it, to use the tool, to tell us, give us feedback, and then continue to build it out.
And then I mean, you have many other tools, but one in particular would be a series of tools in quantum chemistry simulations, and that's such a natural, maybe nearer term application where people can get some real benefit, right? So
yeah, and I always want to be very careful of how I say what the benefit is. So I love the story of Inquanto. That's our quantum chemistry software. We were working on projects with pharmaceutical companies and material science companies and chemicals companies. And to do the project, we needed a tool. And it turned out that the same tool that was useful for pharmaceuticals was useful for material science, was useful for chemicals. And so we built it and we continued to build it out. And then our customers said, hey, what is that? And so we started sharing it with them and they started using it and giving us feedback on it. And then about 18 months into its development, we asked the two questions that any company should always ask their customers, which is, do you find it valuable and would you pay for it? And when the answer came back yes and yes, that became a product of ours. Now, why is it used? If you are a computational chemist, and you know if you are one, if that's not your job, then you're not one. But if you're a computational chemist, you've had classical computing tools at your disposal. That is what you have. But the future is a future that has quantum computers in it. And thinking about whatever workflow you have as you're doing your job, there are times where you can take that workflow and break it into something that you would be able to run on a quantum computer. And we've actually designed it so that you can take it and do it today. So you can take your industrially relevant problem, you can chunk it into a size where then we can run it on today's quantum computers. Not because the quantum computer gives you an answer that you can't get classically, but because it can, because it actually gives you the same answer. And so right now we're at a point in time where you can think about your job, you can think about the work that you have to go do, and you can start to educate yourself on how you're going to do your future work with quantum computers by running them on quantum computers. And so that's where the real value is right now. And we're very upfront about it. We use it because we needed it. We needed the tool that allow us to do it. And our customers right now are now helping us and helping themselves learn about what a future that has quantum computers as a tool looks like, and getting the benefit of, as these quantum computers get better and better and higher performing, you can now run bigger and bigger jobs on them. So it's a really exciting time. If you say when do we cross that threshold for, okay, now you can start doing some things that classical computers can't? In chemistry, we're probably still 3 to 5 years out. So why do companies care? Because most molecules, the development process is about a decade. And if you know, because you've done it over and over and over again, that you have a decade-long development process for your molecules, you are very interested in something that would come in that 3 to 5 year time horizon that would start to accelerate how fast you can do that development. And one of the biggest reasons has to do with patents, right? As you're a company and you're developing a pharmaceutical, you're developing a new material, to protect it, you patent it, and then that patent lifetime starts ticking. And so your ability to actually shorten the window at which point you can develop and have that molecule get released to the world is actually a very valuable thing to take on. And so there are big pharmaceutical companies, big chemicals and material science companies that are willing to put in resources right now to make sure that they can take advantage of this as soon as they can. I will say, because I know I was alluding to it, there are things, though, that have a much shorter time horizon for where we think we will do things that are not possible to do already. So you can do on a quantum computer something that you can't do classically. One area we already do, and that's in cybersecurity. And so we can talk about that in a bit. But there's also a computational area that we're getting very close to, and that is the industry would call condensed matter physics. And it turns out that it's like anything else. When you build a tool and you give people access to a tool, people will be brilliant and they'll find what that tool does really well. And these systems, these quantum computers, are acting like physics systems already. That's what they do. In fact, we have to take into account the change in the Earth's magnetic field over the course of the day in our quantum computer to counteract the noise that would be caused by the change of the Earth's magnetic field over the course of a day. That's how sensitive these systems are. And so they act like physics systems. And if you're trying to model a physics system, you can use a physics system to model that physics system. And so I think we're going to find some areas where we are going to be able to go do things with quantum computers in that condensed matter physics area actually fairly quickly. Within the next, I think, 12 months, we'll start to see that play out.
Yeah, that's really, really exciting because we are so influenced and impacted by all of the things that are nature-based, right? Including climate, some of the big challenges out there. Now we're down to our remaining minutes. So what I'm going to do is I'm going to give a list and just some random areas, and you tell me which ones don't belong of ones you're not working on in some way. So I'm just going to give you a list, and then you check off the ones you think you're not working on. So I believe that you can apply everything you're doing, and you may even be working on this. So, and you mentioned it, perhaps hybrid encryption, blockchain and network security, Internet of Things security, de novo design, which is novel molecular design. So you've talked about some of this already. Drug design and discovery, catalyst analysis and design, new material design, which really works into quantum simulation, network optimization, portfolio management and optimization. And you already mentioned JP Morgan, right? And supply chain and logistics optimization. So tell me any one of those you're not working on.
I was waiting for something that we're not working on. But I would have to say it like this. It's our customers who care, right? So we have done work across all of those areas with customers who are in those areas who care. And they know, and this is one of the most important things about quantum computing right now, which is you have to be realistic about where we are, where the technology is, how fast it's evolving, and when you are then going to be able to take advantage of some of these things. That is step number one. And sometimes people get that wrong. And they get it wrong because they either want to believe something or there's a hype. They feel like they're pressured into saying something that's not true. And so all of this starts with these companies, world leaders in their space, where they know and they've already done the evaluation. And so they're kind of looking for confirmation that when they think it's this particular use case might be 3 years away, this other use case might be 8 years away. They want to know that. If you're saying something else, then you better have a really, really good reason as to why. And there is one place where there is a right now, today solution, and it has to do with security. The threat, the quantum threat of quantum computers cracking encryption in some future scenario, the processes, the underlying quantum physics processes that drive a quantum computer's ability to do that, you can actually use a quantum computer's abilities right now to do something that's the opposite, which is I can make quantum computing hardened encryption keys using a quantum computer to do it. And anybody who's in the cyberspace, I would say very upfront that there's a key and there's a lock, and the lock is the algorithm. And so when we talk about future quantum computers breaking encryption, most of the time people focus on the algorithm, and they should. We need to have post-quantum algorithms. That's why NIST went through this very well thought through process to evaluate potential algorithms that could be considered post-quantum algorithms. But you also have to secure the key. You have to be able to generate provably unpredictable keys in what we call a non-deterministic way, because deterministic means I could figure out what caused that key to be generated. Non-deterministic means there is no way to predict. You can't have a bigger quantum computer that can predict because you've already used quantum physics to your benefit to create these provably non-deterministic keys. And so these are areas where we have really exciting work with customers that they know, because they need to secure data, that they want to use the strongest keys that they could possibly use. And they are either using the latest encryption algorithm, or they're even starting to explore these post-quantum algorithms. Because in that future world, you want to have both of those two together. So those are things that are available now. We use our H-series quantum computer to do it. It doesn't actually have to be running in real time. We use our quantum computer we have to run it for 40 hours to create what we call a seed, a quantum seed, that we can then use to support the generation of these quantum computing hardened keys. But it's the right time. Like people know, especially in critical infrastructure, they are nation state targets, and they are very sophisticated attackers out there. And so there's a concern, and there rightly should be a concern, with how can we use all available technologies, including today's quantum computers, to help do something like that. So that's really, it's a cool part of what we do, and certainly something that's a big deal.
And this is the final sort of compound question, and that is, CEOs always think, well, I can get into the quantum space, start experimenting and running some internal pilots, get the team together and start exploring, and I can do that in 2 months. Or is it like 3 years? And they should be, even though they may not have a practical application yet, they should start exploring, gaining the expertise. Or can they wait to the last minute and everybody else is ahead of them? That's the big players in the marketplace. Like the government as well and things. So you got to start getting some familiarity and building some of this expertise, so that when those ground-changing breakthrough applications happen, you're ready to run. Or can you wait?
Well, you can wait. You just have to be able to deal with the result, the consequences of waiting. And it starts with capacity. Right? When I said we have 2 of our first generation quantum computers, we don't have 100, we don't have 200, we have 2. Why do we have 2? Because our next generation is already built, and our next generation, over its lifetime, is going to be 1 trillion times more capable than our first generation. 1 trillion. It's not 10% better. And then the generation after that, it's also built. We're in the way this works in quantum computing, especially for us, is you have to build these generations overlapping in a way where the development time, the integration time, the testing time happens in parallel. And that one is going to be 1 trillion times more capable than our second generation. So within the span of 4 or 5 years, you're going to have 1 trillion times more capable system. But again, we're not building hundreds of them or thousands of them. And so it really comes down to who is going to get the access, who actually is going to be able to have the capacity, and did you have enough knowledge to then go and implement that in real time? And so there are companies, and they go anywhere from, I have one person who kind of thinks about this part-time, to I have a team of 30 people that are focused on quantum computing algorithm development so that we can put this in as soon as possible. And by the way, when I use that as an example, those are two giant banks. You would think of them as direct competitors. One of them, again, has one kind of half-time person. One of them has a team of 30. And that difference exists across different industries around the world. And the companies that have that really put in those resources and know how to go and deploy this as soon as they possibly can, they're doing it for a reason, and they want to be the leaders. They absolutely want to be the front runners when these systems start to produce, from a computational standpoint, what they want to have them produce. And so again, you can wait. I would suggest that people just have to start getting knowledgeable about it. It's a new technology. There is going to be a need for our children and our children's children to be quantum native. It is a different way to think about the kind of problem set. And the scarcest resource that exists in all of quantum computing right now is the human resource. And it's scarce by a lot. So having those experts who really know what it takes to go do this, and then what applications this would actually be for, and how would you put those applications into practice, that is a very select group of people in the world. And so companies that haven't started yet, I would think they should probably start doing some investigating.
We're headed to 10:01, so I'm going to conclude and thank you. I'm going to say, people out there, you got to look at what you're doing at Quantinuum and follow your work, and you must have some sandbox capabilities so people can start trying and using your services, and look at your open source tools that you have. I mean, you are definitely a leader. I really do want to thank you for coming in and sharing so many of your insights, and in a way that's accessible to the broad audience, right? Everything makes sense. So thank you again, and you bring this wonderful background to this field. So,
of course. Well, thank you so much for having me. This has been a pleasure.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.